So let's continue where we left off. So we saw about signal addition, signal subtraction, and multiplication, and then some other manipulations like time shifting and time scaling. We'll end this with a small example, and then we'll move on to the next module. Okay. So earlier we saw about different kinds of signals, standard signals. A part of that was the rectangular signal and the triangular signal. Okay. Now what we'll try to do is we'll express the triangular signal as a combination of some kind of uh, set of rectangular signals. So remember earlier we had multiple examples where we took a simple function, a simple signal, and tried to represent other complicated signals as different addition, subtraction, scaled, and shifted versions of the same signal. So it was helpful for us because we had to know was how to analyze one particular signal, and the rest of all signals could be completely studied as a function or as some kind of manipulated version of one initial signal. Okay, so this helps us to know about only one signal and then study the rest of all through that one signal that we already know. So what we are trying to do here is now we are going to try and express the triangular function of the triangular signal in terms of the rectangular function. Okay. Okay. So what is the rectangular function? So let's try and recall that first. The rectangular function, as we recall, is just a straight line between minus half and plus half. Okay, and this value is 1. And the triangular function we defined as something which is between plus half and minus half and having amplitude 1. What we'll do is we'll first redefine this. So here if you see the area of this entire function is 1, right? The width is 1, the length is 1, so it's just 1. But here if you try and compute this area, it's going to be, this is 1 and this is just half, the height is half, so the area is 1 by 4. So we'll first try to make the area 1. So if in order to make this area 1, a simple way is to just redefine the triangular function to be of this form. In other words, we'll see the triangular function with area 1 is 1 minus mod t, when mod t is less than or equal to 1, 0 else. Okay, so this is what we'll say the triangular function with area 1 is. Now let's try and get this function through the scaled and shifted and manipulated versions of the rectangular function. So how do we get this? So the question says try and use the integral operation. In other words, what we have to say is, let's say the triangular function is some integral of something here, and that here or whatever that we have inside this integral should be rectangular functions, some combinations of rectangular functions. So how do we get? So let's first, to understand that, what do we get when we integrate the rectangular function? Let's see that first. Okay. If we integrate the rectangular function, so remember the rectangular function is 1 for mod t less than or equal to half, 0 otherwise. So if you integrate this function, and from where to where are we going to integrate? So remember the output of this has to be a function of time. Okay, so in other words, we will integrate this with, we'll just change the variable of integration. So it's supposed to get time as the independent variable after the integration also. In other words, we are going to integrate from minus infinity to t, meaning if you have a function something like this, you compute the area from minus infinity up until time t, and this t, so let's say you first compute the area till this point, and that comes at y, let's say this is t naught, and that is the value of the function y of t at t naught, and then you compute, let's say, the area of this function till this point. Let's call that t1, and that will be the value of the function. So at t naught it will be 0, and y t1, whatever is this area, will be the area of integration. That will be the value. So essentially what we are trying to do here is the area under the curve from minus infinity till the point t is what we'll compute, and then that we'll call as the value of the function y of t. Okay. So what is this? This is till minus infinity. Anyway, the function's value is 0. So it all starts only at half up until t. Okay. Rect of v, which is 1 dv. Okay. In other words, this is going to be just equal to v, which is nothing but t plus half, as long as t is within this limit. So if t is less than half, then what do you think is the value? If t's value is less than minus half, then essentially we are computing the integral from minus infinity to something which is below minus half. The function's value is always 0 there, so it is 0. Now what if t is greater than half? Then if t is greater than half, then this integral you can as well just compute it between minus half to plus half, right? And we know that the area is 1. We just write that it is 1. So this is the integral of the rectangular function. Now let's try and plot this. So if we plot this, what do we get? So t till t is equal to minus half, the function's value is 0. Okay, and from minus half we start the non-zero values of this integral function. So at minus half it is 0, and then at t equal to 0 we get half. And what about the values in between? It actually starts linearly increasing, right? It goes like a straight line because it is t plus half. Okay? And at t is equal to half, this is equal to 1, and beyond that it's just 1. So this is the integral of the rectangular function. Okay. Now if this is the integral of the rectangular function, how are we supposed to get the triangular function from this? At least one portion that we can see here is from minus half to plus half. This looks like the slope of the triangular function. So somehow if we can get only that portion, then we are done. So then we can say that, okay, this is the function that I'm looking for. But also remember, this is from minus half to plus half. So there are, as I've said before, when you are trying to express one signal in terms of other signal, there are multiple possible ways. So even in this case, there are multiple ways that you can represent the triangular function using the rectangular function. I'm just going to show you one particular example of how to do this. So one easy trick is to use two rectangular functions, okay, one of this form, all right, such that it is starting at minus 1 and ending at 0 with, so what if we integrate this? Of course, if we integrate this, we'll get 0 till minus 1, and at minus 1 to 0 we'll get this triangular portion, and after that we're going to get a straight line. which is exactly corresponding to this. The left hand side of this integral corresponds to the left hand side of our actual triangular signal. So at least the left hand side portion is nice. Now, how to get the right hand side portion and how to remove this straight line over here, okay? So this is what we'll try to do. Now, what if we take a rectangular function which is of this form, where it is starting at 0, ending at 1, okay? But then its amplitude is minus 1. If you integrate this signal, what would you get? Okay, so clearly till 0 there is nothing, the area is 0, okay, but after that the area becomes non-zero, but then in the negative direction, okay. So it means that it goes down like this, and then it remains a straight line which is minus 1, okay. So now if we somehow add these two, let's say we are adding these two, what do we get? The left hand side for this signal is 0, so the left hand side of this signal will get as such, and the right hand side is the region where it gets added up. So wherever there is minus 1, just cancels this plus 1. So wherever in between, so we have 1 minus t, this slope, okay, which exactly gives us what we have here. So this is what we are looking for. Once again, this is only one particular way of obtaining it. There are multiple ways of obtaining it, but this is one particular way of obtaining the triangular signal from the rectangular function. Okay, so now it means that I have to get this portion and this portion. Now, how do we express these two portions? Basically, what we are trying to do here is shifting. All you have to do is just shift the rectangular function to the left. If we have to shift the rectangular function to the left, what do we have to do? Just add in time. How much? Just by half. And how do we get this signal? That is rectangular function shifted to the right, which means it's negative, and the amplitude is also flipped, which means there is a minus here. It's as simple as that. That's it. So you're done. And this is the order of, this is the integration. Okay. So what we have done here is essentially express this triangular function in terms of the rectangular functions that we already know of. Okay, so this way there are multiple combinations of different signals that you can express for a particular given signal. Earlier we expressed the rectangular function itself as a function of one particular triangular function. Now we have expressed the triangular function as a function of the rectangular function. So this way what we can do is, given any x of t, we can express that as some combination of, some combination of y of t. So when is this useful? So if I know everything about y of t and nothing about x of t, I can completely study and analyze x of t just by knowing y of t, because I can say that I can obtain x of t completely through y of t. So if I know the properties of y of t, so if I know how, let's say, a particular ingredient tastes like, then anything that you make out of that ingredient alone, you can also know how it will taste like. That's exactly what we are trying to do here. We know the ingredient y of t. So because I know how the ingredient y of t tastes like, if I know how sugar tastes like, any chocolate that you make out of sugar, you can also say how it will taste like, because you know what all it is made up of and you know the taste of all the ingredients. So because you know all these things, you are combining that in a particular fashion, and this will tell you, or from that you can also tell what the combination of all these ingredients will also taste like. That's the usefulness of expressing one in terms of the other signals, or expressing or decomposing a particular signal in terms of other well-known signals. Okay, in this decomposition, we have been so far saying only real valued signal. So now what if we have a signal like the sinusoid, right? One of the important standard signals. Now we know that any cos theta can be written as e power j theta plus e power minus j theta by 2, okay, where j is nothing but the square root of minus 1. So electrical engineers always use j instead of I. So we don't use I as square root of minus 1 because often we get confused. The notation I is also used with for current, so we don't want to get the confusion between current and the imaginary number. So we don't use I. So we stick to representing the root of minus 1 with j. So there is this representation, which means we can say that cos omega t is half e power j omega t plus e power minus. So we can decompose the sinusoid like this, even something of this form. Now all the earlier decompositions that we saw was in terms of only real valued signal. Now what we are trying to do see here is a real valued signal here on the left hand side is expressed as a decomposition of two complex valued signals. Does this really make sense? Do we even want complex signals? We'll end up seeing almost 50% or more than that of this course will be using complex valued signals. So complex valued signals representation is so useful for us. Why is this so useful? What does it actually model? So whatever we have been doing so far is trying to model a real life practical setup using some mathematical representation, and then we'll analyze the system using that mathematical representation. So that means this is a representation. This complex valued signal is a model. It is a representation of something which is happening in real life. What is that, and why is that necessary for us?